So today in factories and in robotic arms, the visual inspection system can detect a hairline crack on a very small gems in M&M size field, moving at a very high speed conveyor belt in real time. And the story is convolutional neural network. So before just touching on CNNs, I will try to make things more clearer why we need CNNs. So before CNN, detecting a cat in an image will require to create a neural network, which takes the 1D array and detect the output. So it is like converting the image, which is just a number from a computer, for a computer from 3D, that is a height, width, and their color channel to 1D. So it is like this image, which is here of a cat, is being converted into a array of numbers, which is the pixel information, and it's being converted into a 1D array, and then this array is being given to the neural network, and we try to expect the output from this neural network. So with this method, there was the flaw that the accuracy was below 45% to 40%. And the primary issue was the spatial information loss. So what is spatial information loss is, so this pixel of a cat and this pixel of a cat and this pixel of a cat and this pixel of a cat, or sorry, this pixel of an image are correlated because all these pixels relate to the cat. But this pixel here and this pixel here does not been related to the cat, but it's been related to the image, but is not been useful for our detection. But when we try to convert this 3D image into a 1D array, and 1D array is being passed to the neural network, the neural network never knows whether the pixel which is being seen here belongs to the cat or does not belong to the cat, and it's just will fail eventually when a new image is being put to test on the neural network. So this was the pretty much issue with the CNN. And so on 90s, Jan LeCun created convolutional neural network with the help of convolution operation. So it is a method which before converting the pixel array from 1D, try to find the very useful features and only features which can help neural network to understand or to detect how a cat looks like, or how a cat looks like in the image, or in order to detect as an output. So before CNNs was mostly being used so that it can help in 3D images, because sometimes in 2D images we can still it can still be useful by using 1D, because we have blacks and whites only, the shades of black and gray and white. So the image can still understand the pattern here, that it belongs to the number 8, it belongs to the number 8, because these pixels have higher intensity and these pixels have lower intensities. But with 3D images like this cat, it has been very difficult to understand how the cat will look like, because the color of this cat here and this thing is pretty much similar. So it has been more difficult to understand how which part of the cat has been different to the background. So for that, CNN has this architecture. So CNN has basically three operations, that is convolutional operation, ReLU operation, and a polling operation. The convolutional operation does some mathematical functioning and it's been passed to the ReLU activation function, which tries to uh, remove all the negative pixels, and then the feature map is being given to the polling operation to reduce the map feature map size, and it's being done continuous times in order to get a very useful feature map. And then once we have a feature map ready, we can flatten it out, and then it has been just passed to the fully connected layer, that is a neural network, and it's been connected to a softmax layer, which help us to find whether the image has a cat or a car or a truck or a van. So This is pretty much how the CNN has been architectured here. So we have CNN operations. We have three CNN operations. The first CNN operation is convolution operation. So in convolution operation, a small matrix, say a 3 cross 3 slides over an input image. So this small matrix is a special matrix which does some multiplication and summation, and it tries to find the required feature. For example, if we have an image of a face of an human, it can easily detect the features just like eyes, nose, ears, mouth from the image by having a different filters on different part of the operation. So you can easily detect how the eye or how the nose or how the lips will be look like human face. So we can have multiple small matrices for this, and these small special matrices are called filters. So there are multiple different types of filters which help us to find different things like edge, curve, textures of the from the image. So for an example, if we have an input image, this if we have an filter which is being used to find the horizontal edge. If we try to use this horizontal edge filter and we have all the middle row as 111, we can easily find the horizontal edge. And if we want to find the vertical edge, if then we can make the column as 111 and we can find the vertical edge from the image. So this is pretty much how the convolution operation happens. This is a very higher level of how the convolution operation happens. After convolution operation happens, we then pass this feature map or feature image to a ReLU activation function. So this ReLU activation function has been like you have an input image. Let's say you have an input image of a car, and you do some convolution operation, and then this is your feature image. So your feature image has a car and has some background and something, but still we don't have a focused car here. So in order to get the focused car, we need to remove the negative pixel from the image, that is these pixels, and then these negative pixels, once removed, you can easily see that the car is been here. So apart from as input image, the background color and the car color is very similar. We're still able to find the useful feature of the car, that is the shape of the car, very much from the ReLU activation. So the ReLU activation function basically removes the negative pixel from the feature maps and gives us the output as zero or maximum, as this helps in learning the complex patterns. And then this activation function output is being passed to the polling operation in order to reduce the map size. So we take a 2 cross 2 or n cross n window from a feature map, and we just take out the maximum value or average value of that 4. And just for example, if we take uh, a 4 cross 4 matrix and a 2 cross 2 window and slides over it, and we can find that the maximum value here is 6 is being used, or we can use the average value, that is 4.5 here, and it's been used here. So we can reduce this feature map of 16 cross 16 to a 2 cross 2 feature map. So it also helps us in basically tolerant understanding the small shifts. So if a cat is 2 pixel left or a cat is 2 pixel right, we can still be able to detect that. And this has been done multiple times here and there until we are not ready with the very useful pixel feature map. And then we just convert it into a 1D array by using a flatten operation. And this 1D array is being passed to the neural network, which is have only the useful features, which is then being passed to the softmax operation, and we can able to detect whether it is a car or truck or a van. So before moving on the code part, I would like to tell you what is MNIST dataset is, which is being used here as an example. So MNIST dataset is basically handwritten numbers from 0 to 9. in order to train the model to understand how human writes number. So it is having a 10 class, which is being used on the further coding for training the model. So before moving on to the model, I would like to show you how model is being written inside, how the operation has been written inside. So this is mostly in a model file. We have a convolution layer. We have a convolution operation. We have a ReLU activation function operation. We have a max pool operation. Then we have a flatten operation, and then we have a feed forward layer. So as we have discussed, the convolution operations work is to basically find the useful features. So we try to do some mathematical operation, that is multiplication and summation, and that gives us the feature map. This feature map is then passed to the ReLU activation function, which gives us maximum value or zero value, and try to remove all the negative values from the system. And then this ReLU output feature map is given to the max pool layer, which takes a window of n cross n and try to find either max or average. So here we have used a max pool layer. So we have used np.max to find the maximum value from that window. And then this output is being just flattened out into the shape of how neural network understand. And then the output is being given to the feed forward layer or neural network layer. So this is pretty much how our model is being written from inside. And moving on to the code, this is pretty much the skeleton ready. And I will just show how the model is being architectured from inside, not just like we create each class of operations and then we try to train the model by these type of method. Uh, PyTorch has already PyTorch and TensorFlow has already helped us a lot with these things. So we basically you are using an MNIST dataset here, which I've shown previously, which gives us X10 Y and X test Y test like pair of the images, which is, and it's been reshaped so that it can be on the form of how neural network will take it as an input. And we have a 28 cross 28 size of image. So how the models being written can be like on TensorFlow we use layers. So layers class has all the operations. So first of all we have to do a convolution 2D operation. The convolution 2D operation requires 3 cross 3 matrix, and then an activation function following that will be required, that is will be a value. And we on the uh, mode we have to pass the input shape or input image, input shape of the image, and further it will just take it from the intermediate layers. So we have 28 cross 28 and a grayscale image, that is one channel image. Following this operation they will be doing a max pooling. So max pooling 2D operation, which will be of 2 cross 2 size, and then it's been done a few of the times. So we will be doing it only 2 times. In order to get more features, we will double the convolution operation size to 64, and we will just remove the input shape from here. And now we have a convolution 2D layers ready with max pool layers. We will just flatten it down to 1D layer, and then we need to just pass it to a neural network that is of 64 neurons, and an activation of ReLU in order to remove the negative pixels. And at last, we will use the softmax layer to find the 10 class probabilities so that we were able to detect it very much, um, which class has been on the image. So this is pretty much how we write the model here, and let me just start it down. So we have used a loss function here as a categorical cross entropy because it is having more and more classes, like 10 classes. If we have only few of the class, two of the class, then we can use binary cross entropy. But we have 10 classes. We are using categorical cross entropy. And we are using 10 epochs. So 10 times that the model will move forward and backward and forward and backward. And we have used 128 as a batch size and with a validation split of 10%. So if we have 100 images, the 10 will be used as the validation. So this is how pretty much your model has been architectured. So we have like 121, 930 parameters model ready. So it is like 1,21,930 parameter model to detect the MNIST dataset. Condition to the operation followed by max pooling, then again same, and then flattening and then passing it to the neural network, and then the softmax layer. So the model is being trained. The 10 epochs were very fast because it's been run on the GPU. And we have the model accuracy as 99.05%. It is 99%. And also the text test accuracy as 99%. So the model has 99% accuracy of understanding the handwritten numbers of human. And in order to understand what is been happened there inside, has all been the black box for us. I've just tried to write the feature map after each operation on convolutional layer one. So this is the input image which has been passed, and you can see the 32 feature maps, the 32 which we have written here. So the 32 feature maps is being created inside. So after first filtering, we have this number, this is as 8, and up till the last we were able to detect the 8 only as the feature values, and rest all will be neglected. So after this convolutional neural operation, we have pretty much information about the 8, and then it's been passed to the model, and so the model get trained on the information of 8, and similarly for all other numbers. So this is pretty much how the CNN works.